Hello, everyone. Welcome back from the break. So now we have Rahul Singh that will tell us about algebraicity of CMC surfaces of revolution.
Thank you very much. First of all, I would like to thank the organizers for giving me this opportunity to present my work. So today I am going to talk about this algebraicity of CMC surfaces of revolution. In general, I'm going to talk about algebraic surfaces in Euclidean spaces and three-dimensional non-Minkowski spaces. So I will start with some definitions and then I will also kind of give you a history, a brief history of the problem and the work. And finally, I will explain my work. Okay. Yeah, so E3, this E3 will always denote this three-dimensional Euclidean space. This is the metric, and the L3 means this R3 with this metric. There is a minus over here. And yeah. So now what is a regular algebraic surface in R3? So we say surface S is algebraic in R3 if it can be seen as a zero set of some polynomial and also with the extra condition. So if you just think about this, then the set S, you will say this is an algebraic set, the surface. And if you add this condition that the non-vanishing of the gradient at every point of the surface S, then it's a kind of tells you that it's a regular. So that's all. So a regular algebraic surface means we mean always this, that the set is defined like this. It can be seen as a zero set of some polynomial and the gradient is non-zero everywhere on the surface. Yeah, and this, of course, this P is some polynomial in XYZ. And this degree of this polynomial is what we call a degree of the surface. Okay, so in particular, one can see that these regular algebraic surfaces are going to be properly embedded. They will not have any self-intersection. And this follows from regular values theorem. Yeah, so our surface, which I'm going to, so when we say regular algebraic surface in R3, that means you're not going to see any intersection or they will not self-intersect. Okay, so what is a minimal surface in E3? E3 Euclidean space. If its mean curvature function vanishes identically, we say it's a minimal surface. And we simply say it's a CMC surface if the mean curvature is constant, non-zero constant, identically at every point. Now, let me briefly introduce what this Lorentz-Minkowski space and how the objects are defined there. So we say a vector in L3 is a space-like if if this, because you can see the metric had this negative signature. So at some time for some vector, this inner product will give you a negative number. So whenever this happens, we say that such a vector is time-like. If it is positive, we say it's a space-like. And yeah, if it is, by definition, the zero is chosen to be a space-like vector. And yeah, the light-like vectors. So we are not going to, so in our situation, we are just, although we are talking about this L3, but our objects of interest are going to be just space-like surfaces. I will say what are they, but yeah. So before that, what is a space-like curve in L3? So we say curve is space-like if the tangent vector at every point of this curve is space-like, and it is time-like if the tangent vector at every point is time-like. Okay. Now suppose we have two-dimensional subspace T of L3. L3 means R3. We say T is a space-like if the induced metric is positive definite. So you have a plane in R3, and then you have a metric, this Lorentz-Minkowski metric. So when you induce the metric on the plane, the metric is positive definite. In some sense, it's Riemannian. Okay. So we say such a plane is a space-like plane, and we say a surface is space-like. So if all its tangent planes are space-like. And yeah, analogously, we have this definition. So what is a space-like surface S in L3? Sorry, what is the maximal surface? So it's a space-like surface. The first condition, it has to be space-like. And the mean curvature function, again, it should vanish identically. And yeah, we say it's a CMC surface if H is non-zero constant identically. Okay, so now let's look at the history of this problem. So when H is zero, that means mean curvature is, that means when we are looking for minimal surfaces in Euclidean space, three-dimensional Euclidean space, there are plenty of examples, in fact, many examples of surfaces which are algebraic. So the simplest example one can think of is the plane, the affine plane. So you can write down a 1-degree polynomial in one variable so that the zero set of that 1-degree polynomial will give you the plane, and that's a degree 1 surface. So what I'm saying is simply this. So, yeah. So I'm saying this. Just so you can take this P to be this polynomial where this is non-zero vector. So if you look at the zero set of this will give you an affine plane in R3, and that is an example of a algebraic surface, which is also minimal. Okay, and the next example is of this NAPR surface, and you can see that this is the polynomial which describes this NAPR surface, and if you look at this closely, so you can guess the degree will be 9. So degree of this NAPR surface is 9. So what we have said already, a definition. So this NAPR surface is an algebraic surface. So you can see if you look at the zeros of this polynomials, they will the points will lie on the NAPR surface. So this describes NAPR surface. So by definition, NAPR surface is a algebraic surface. But the point here is that this, although it's an algebraic, it's not regular in our sense. Because if you look at this, what is the definition of regular algebraic surface in our case? We say it should be expressed as a zero set of some polynomial like this, and also the gradient function should be non-zero. But what happens if you try to compute its gradient at 0, 0, when you have x, y, z, you choose this to be 0, this is a point on the NAPR surface, but this that fails to be regular in that sense. So it is a not regular algebraic surface. So this is, although this is a degree 9 polynomial, it's a minimal surface, it's algebraic, but not regular. Okay? And the same is true for Henneberg surface, which is a degree 15 surface. That means you can write down a degree 15 polynomial whose zero set will be a Henneberg surface, and it's not regular. In fact, this is a fact that there are no regular algebraic minimal surfaces in E3 except plane. So the plane is so when I say regular algebraic, we always think about that definition which I have shown you in the first slide. So yeah, so plane is the only example. So if you're just searching for this minimal surfaces which are also regular, algebraic minimal surfaces which are also regular in the sense which we mentioned, then the plane is the only example. And you can also see the other two examples which I have shown you here, they are not regular, although they are algebraic. In fact, again, there is a theorem of that you cannot have a minimal surface having whose degree will be less than 5. So anything if you are looking for, yeah, it is not going to be anyway regular, but even if you're looking for some simply algebraic minimal surfaces, then you will not find a minimal surface having degree, let's say 4 or 3, and or 2 even to say. So yeah, so degree 1 polynomial. So this is the regular algebraic surface. Yeah, so Yeah, so this paper by Perdomo is the starting point. In some sense, you can say that where he considered this CMC surfaces in E3 of order less than 4. And he showed that the only constant mean curvature surfaces which are algebraic, degree less than 4, are the planes, the spheres, and the cylinders. So this is what he shows in that paper. So yeah, so you can see, so it's not the, you can say it's a complete, it just tells you about the degree less than 4. What are the examples? Now again, when H is, again, since we are just discussing this constant mean curvature, so now when H is constant, again, the non-zero, the Barbosa and Docamo, they have shown that if you're just looking for the regular examples of algebraic surfaces in Euclidean space, then the only examples are spheres and right circular cylinders. And the proof crucially uses, there's something called a structure theorem for CMC surfaces. It is very, so when I'm saying structure theorem CM surfaces, that means there is a structure theorem which exists for properly embedded with finite topology CMC surfaces. There is such a theorem which tells you about, means if you're having a CMC surface, regular CMC surfaces, which is properly embedded, having finite topology, then actually you know how it ends will look like. So he uses that theorem to arrive at this theorem that the only examples of these regular algebraic CMC surfaces in E3 are the spheres and the right circular cylinders. Yeah, it is just an observation which is going to be kind of crucial for us, what we are going to show. We can immediately see that these spheres and cylinders, they belong to a special class of surfaces, surfaces of revolution. And this class, of course, includes other examples of CMC surfaces which are called unduloids and nodoids. They're also called Delanois surfaces. So let me just briefly say what is this Delanois surface. So you might have heard of this. So you have conic sections, and then you take a line, and then you try to roll this conic section on that line without slipping. Then if you look at the focus of one of its like conic section, then you just consider the locus of one of the focus of a given conic section, and that will give you, in one case, it will give you unduloid and nodoid. So what I'm saying, so like for example, you have a line, and then if you think of an ellipse like this, and then you choose one focus, and then you kind of rotate it without slipping, whereas then you look at the locus of this. So if you just try to follow this locus, not exactly the same. This is something, some curve like this will appear, and this curve, what we call is undulary, and it is, and when you, yeah. So this is a curve in, of course, in a plane, and when you rotate it, you will get a surface of revolution. I will talk about these things later on, but yeah, and how to get so when you rotate this undulary, this curve, you can imagine a surface of revolution generated by this curve, kind of, yeah. So that is what we call unduloid, and when you have a hyperbola, and then you do the same thing, you choose one of the focus and look at its locus when you revolve or move it along this line, you will get something called nodoid, and this will be the kind of, you will see something like this, and then when you rotate it around this axis, you will see, you will get what you call the nodoid. So what I'm saying that spheres, of course, spheres and cylinders, they are the examples of surface of revolution. For example, you can just draw a line parallel to that line, and you just revolve it, you will get a cylinder. And then, in fact, if you try to think of how spheres fits in this family, so it's not just exactly one sphere, it is a sequence of spheres which are like kind of making a cusp at certain points. So you have sphere there. So these kind of, and of course the plane is also there. So plane is also an example of a Delaunay surface, but that's an example of zero mean curvature. Yeah, so this class, yeah, so this is an observation. Now, again, in this 2019, the same author, the Perdomo and this Chegg, showed that there exist no degree 3 algebraic hypersurfaces in the Euclidean space when, in fact, n greater than equal to 3. So, in fact, yeah, when I was telling that De Carmo and Barbosa have obtained this result about there are no regular algebraic hypersurfaces in Euclidean space except sphere and cylinder. The same question, there is a generalization of this question problem in the same paper by De Carmo and Barbosa, where they asked what in higher dimension, if you go in like say in Rn, or let's say Rn plus 1, can you say that if you are looking for, searching for regular algebraic hypersurfaces, what are the examples? So the conjecture was, in fact, yeah, it is, that the only example of constant mean curvature regular algebraic surface in, let's say, Rn plus 1 are n-dimensional spheres or the cylinders. Okay, so, but yeah, there's some progress I will mention here towards that problem. But yeah, so this is, so in this paper, yeah, so what they showed, that there exists no degree 3 algebraic hypersurface in the Euclidean space. Yeah, that is kind of, so now you should see that we are not saying anything, they're not saying that regular, they're just saying algebraic hypersurfaces. So those surfaces might have, they're not saying that they're just looking for regular surfaces, regular algebraic. It can have intersections. Yeah, so this is what they have done. And yeah, very recently, in 2022, these 3 mathematicians, they have shown that there are no regular algebraic hypersurfaces with non-zero constant mean curvature defined by polynomials of odd degree. So if you it says if you have an odd degree polynomial, this cannot be you cannot have a regular algebraic hypersurface which can be seen as a zero set of an odd degree polynomial. In fact, they have also shown that the hyperspheres and the round cylinders are the only regular algebraic hypersurfaces with non-constant mean curvature in En plus 1 defined by polynomials of degree less than or equal to 3. But again, their assumption is that degree has to be less than or equal to 3. Okay. So yeah, so this is kind of partially answers the questions the posed by De Carmo and Barbosa. But yeah, if you think about this study of this in general algebraic CMC surfaces may not be regular. And of course, in other ambient spaces like L3 or extra is a basic question that has very little progress. Yeah, so there exists a complete classification we can say now. We know for regular algebraic CMC surface in E3, not much is known for if you try to think of just general algebraic CMC surfaces, need not be regular in E and in general. But again, there is a paper by this mathematician where he kind of gave a classification of something called semi-algebraic CMC surfaces in E3 with singularities. So algebraic, so you can think of semi-algebraic surfaces like they are given by one polynomial, zero set of one polynomial, and then you have a bunch of polynomial with condition that they are everywhere positive. So union of, if you have a collection of such polynomials and you take the union of zero set of those things, and that is what we call semi-algebraic. And clearly, if the algebraic sets are semi-algebraic, right? The way. So I'm not giving you the definition, but yeah. So they have studied, so they have allowed singularities also in their example, and then yeah. So this is the what I know about the progress in this area. Okay. So now let's come to the objects which I am going to focus. So before I say what we have done, at the end you will see. So basically we are going to study this. We are going to focus on CMC surfaces of revolution in L3, space-like. Okay, I have already explained what is a space-like means. It's like space-like CMC immersions are almost like they're analogous to the CMC surfaces in E3 because the induced metric is the Riemannian metric. So it's like but anyway, so before that, so it would be of course a natural question to investigate all regular algebraic space-like CMC surfaces in L3, as we know that they are the analogous of the CMC surface in 3. But as it turns out, this is not very, you can say, easy at the moment because unlike Euclidean setting where there was a structure theorem for such surfaces and one could they applied that to prove their result, we do not have such a, at least I'm not aware of such a result. So we do not have some classification of that sort for for regular space-like CMC surfaces in L3. So it's so what we are going to do. So, but like as I mentioned before, what we realized there that those examples which the sphere and the cylinders, they were kind of surfaces of revolution also, and they were algebraic. They are the only examples. So in this case also for L3, we are going to just focus on the CMC surfaces of revolution, space-like CMC surfaces of revolution, but around, because now when you're in L3, you have if you take a line, it can have a different causal character. So you have to kind of think of surface of revolution along each such axis, like if it is a time-like axis. So like you see, so what I'm going to consider now is CMC surfaces of revolution about a time-like axis and a space-like axis. Of course, one can also talk about what about null axis, but I have not considered that in this paper and this work. But yeah, I will just talk about what happens to space-like CMC surfaces of revolution when you consider them about time-like axis and a space-like axis in L3. Okay, so yeah, so this is kind of this observation kind of motivated us to let's try to first study if we can say something about this algebraicity of this space-like CMC surface of revolution in L3. And yeah, so in fact, what we showed that in this class, the only examples are space-like cylinders and the standard hyperboloids. So they are algebraic. So I will first explain you I will say what are the key points in the proof. So the first point is there is something called Kenmotsu type parametrization. There is something called Kenmotsu type parametrization for CMC surfaces of revolution, or in general surfaces of revolution in R3. There exists such a. So first we would like to show that we have such a parametrization for CMC surfaces of revolution in L3, and this is the first point. The second point is like once you have a surface of revolution and if you look at that parametrization, using that parametrization, one can associate an elliptic curve. So I will say it's just what is an elliptic curve? So it is if you say some degree 3 polynomial in 2 variables, it's a specific form. Yeah, there are many ways to talk about elliptic curves, but yeah. So yeah, and the third point is for once you have an elliptic curve, associate an elliptic curve. And somehow we were able to also show that the elliptic curves which you are going to get, they are going to have a non-zero discriminant. Meaning is the elliptic curve in general, they're not as smooth. They can have singularities, but in our case, the all elliptic curves which we are getting corresponding to some CMC surface of revolution, they are going to be smooth. And once you have an elliptic curve, a smooth elliptic curve, again, this is a fact that you will get a Weierstrass P function. Weierstrass P function is just simply a doubly periodic function. So whenever you see an elliptic curve, you see a Weierstrass P function, a smooth elliptic curve. And the last point in the proof is that if you have a Weierstrass P function, this is a transcendental function. So, and cannot satisfy any algebraic relation. So a function is said to be algebraic if you can write down some algebraic relation which is satisfied by this. If this happens, you say the function is algebraic. If it's not, then it is transcendental. So it is again a known fact that the Weierstrass P functions are transcendental. Yeah. So let me start with this, showing you the in a very special case, I am just showing you the parameter, but the Kenmotsu work is, he has derived a very general parametrization, but for our purpose, when you assume that your CMC, you have a constant mean curvature, you have a very simple parametrization. So the thing is so you start with a arc-length parameterized curve, and you can assume that this coordinate is always positive. Then you can write down this parametrization for surface of revolution, where this theta is the rotation parameter. So this is the parameter. So you assume, so you start with this parametrization, and then what Kenmotsu has shown that the generating curves. So because when I say starting with this curve alpha s, this is the generating curve for the surface of revolution. This will generate the surface of revolution. So this x of s and y of s can be computed like this. So you can see that's just a function of, they depend on this h. So yeah, of course, h is assumed to be constant here. And this b here is, this b, which is a constant, real constant, is allowed to vary between 0 and infinity, 0 included. Now this b is a kind of, so for every value of b, you will get one CMC surface of revolution. So for instance, when you take b is equal to 0, you can see when b is 0, what you will have, this term will be some, you will get a line parallel to the axis, y-axis, when b is 0. This y coordinate will be constant, right? This is 1 by 2h when b is 0. So for b equal to 0, you are seeing a cylinder. And when b is 1, you will get this sphere. So for when b is 0, you get cylinder, and this is surface of CMC surface of revolution. And when b is 1, you get a sphere. Now, when b is in between 0 and 1, those values will give you this undulates. So for b belongs to open 0, 1, gives you undulates, and when b is greater than 1, this will give you this nodoids. So these, yes. So basically you are just getting these curves, parameterization for those generating curves, so you know the corresponding surfaces of revolution. Okay, so yeah, so this was, so in this paper, they have done it for any, you start with any, if you have given a mean curvature function, you can always write down a parameterization like this. But this is a very special case. Okay, yeah, this is what it is. So b is equal to 0 is a cylinder, and cylinder is an algebraic surface because you can write down algebraic relation equation, which zero set is this. Yeah, this is, yeah. So this was the Kenmotsu parameterization. Now we would like to have a similar parameterization, because that parameterization is the key. From that, we are going to get elliptic curves. So what are these parameterization for Delaunay surfaces? So like I said, we will be considering two classes of CMC surface of revolution. One is around x-axis, and the next is around z-axis. So suppose if you have a space-like curve, again, space-like curve, you know what is the meaning of this? That means it's everywhere the tangent vector has positive length. And yeah, again, this has assumed that this condition tells you that this curve is not intersecting the axis about which it is rotating. And then we can write down the parametrization for corresponding surface of revolution about x-axis like this. So this is how the parametrization would look like. And then we can show, in this case also, we will have a formula like this for the generating curves. So yeah, this is what we showed. But yeah, this was also done by this Ishihara and Hara in their paper. They have done it in general, like following the Kenmutsu's work. But yeah, for our case, since this was needed, so we derived it here. But yeah, this is also done in, you can find here. So, and again, in this case, so you have this, and now in this case, if you look at this b equal to 0, so b equal to 0, again, it is giving you the space-like cylinder. So it's a cylinder. So so we are calling it a cylinder because, because whenever you think of a surface of revolution in E3, you think about a circle kind of thing, like you're rotating along a circle. But in L3, due to this metric nature, you can have circle like this also. So it's like a kind of, you can think of it's like a circle in this L3. And this, and b is equal to 1 gives you a standard hyperboloid. Yeah, so this is and you can see that these are algebraic. So a space-like cylinder is an example of an algebraic CMC surface, and then b is equal to 1. Yeah, z coordinate is positive. And then you will have for b, again, from between 0 and 1, you will have this analogs of unduloids and nodoids. And yeah, this was also discussed, just to mention that this was also discussed by Nomizu and Hono. So, but they just considered this surfaces of revolution with constant mean curvature surface in Minkowski space. So now we will have a similar kind of parameterization. We can write down the formulas for the generating curves. If you change the axis about which you're rotating. So now instead of x-axis, suppose if you have a z-axis, which is a time-like axis, and if you now take this generating curve, and if you revolve it around this z-axis, we can compute this. Like the axis will be given by this and this. And again, this b. So again, but now in this case, something interesting is happening. So in this case, when b equal to 0, you're not getting a real cylinder, real space. Like you're getting imaginary. So you can say you have a complex cylinder. So x and y can be complex now. So this is something which is very peculiar or specific to this Minkowski space. So for b equal to 0, you are getting an imaginary cylinder because you can see that this equation doesn't have a real solution. And this b equal to 1, again, but you have a standard hyperboloid, but now x is positive. Yeah, so in any case, so in this case also, you see, you have these examples. I will just briefly outline in fact, I've shown you the proof is very straightforward, but yeah, some trick is needed. So how to show? So I'm just going to show you how we obtained this formula, this x for x's and z's. So we start with a parametrization like about z-axis. The same can be done for x-axis also, but let me just show it for z-axis. And then we can compute its first and second fundamental form like this. Okay, and then you can write down the formula for mean curvature function. And when you compute it, since h is assumed to be constant here, you will get an ODE like this, a second order ODE like this. And then you can multiply this equation by this and this. And also we are also going to use this fact that, because you see, initially I said we are starting with an arc-length parametrized curve. So an arc-length parametrized curve is which has unit speed, right? So, but in this case, since the curve is in the xz plane and z has this minus sign there, so this is the length we are looking for. So we have this relation. So using these two things, we obtain these two simultaneous ODEs. And yeah, so now what we want to do, like we want to solve for xs and ys. So what we are going to do, we had this second order ODE. We would like to if we will see if we can reduce this system of, or we can combine these two equations to a single ODE. So for that, as it turns out, if you introduce this T split complex number, so what is split complex number? They are the numbers of this form where k is defined to be k square, but defined by k square is equal to 1, and then that k, we can also define its conjugate, which is given by this, and in this case, the absolute value of t will be given by this. Also, for this split complex number, the analog of Euler's formula holds. So this is kind of Euler formula. And now, once you have seen this, we will introduce or we will set this Ws to be this, and then those two ODs which I showed you before in the previous slide, it turns out to be, you can show that this is equivalent to a single first order ODE, you can say split complex number. And yeah, in fact, the equivalence can be seen like this. You have to just simply expand this, and then using the properties of split complex number, you say that the vanishing of this, or this ODE is equivalent to these two. Oh, sorry, there is a 0 here. Okay, so what to do with this ODE now? So this is the ODE we are looking at. Now let's see what happens at h equal to 0. So when h is 0, you will see this term will, this will not be there, and now you can easily write down the solution for this, and the solution will give you in this case, an elliptic catenary. So you get a catenary, elliptic catenary, which is like given by this, and now when you rotate this around z-axis, this will give you a elliptic catenoid, and which we know it is an example of a maximal surface. So it's a zero mean curvature surface, and obviously this is not an algebraic surface because you can see that this function is not algebraic. It's not a polynomial. And so when h is non-zero, yeah, so what happens when h is non-zero constant? The solutions of this are given by the formula which I had shown you in the this slide. So when h is non-zero, these are the solutions.
Sorry, can you go back to the previous slide? So here you have this formula which has the Singh squared. Yes. So you say, well, of course, this formula is not algebraic, but how do you know that there isn't some other formula, possibly very high degree? So if you just prove, there's a formula which isn't algebraic, doesn't mean that the surface isn't algebraic. I mean, how can you rule out there's some degree 1000 polynomial whose zero set is that surface, right?
So you're saying that by doing some local change of coordinates, you can go into...
Well, not just...
But in that way, it is always true. Like if you have a smooth surface, you can always do some local change of coordinates. So in that local change of coordinates, it will look like an algebraic set.
I wouldn't want to change coordinates, I think. Oh, that's the argument you say? Well, even...
You can make a change of coordinates too, so that it will... So it's a general fact. Like, of course, you have to do a change of coordinate, and then you will see every smooth thing will look like...
Yeah, of course, when you change... I don't want to change coordinates. I want to have some different polynomial in 3 variables.
I think...
I mean, I think maybe it's trivial, and are too sleepy. But some people, you know, they give you obviously in elementary differential geometry that you say, here's a cone, right? X squared plus Y squared is Z squared. And then they say, well, prove that the origin is not regular point. And then, of course, some people say, oh, it's clear, use this equation, and I see it immediately, it's not a regular point. But then you say, well, there could be a different equation, you know, describing that cone, which makes it a regular
So I think...
How can you rule this out, right? That is essentially the gist of my question. Now, you guys seem to have an answer. Oh, maybe not, I don't know.
So I think if something is, we are calling, something is not algebraic in one, and if you want to remain in the same coordinate system, then...
Yeah, I tend to believe this is not algebraic.
Yeah.
I agree, but I'm just wondering, how can you be so sure by just saying this equation describes it, it's not algebraic, fine, I'm done. Then I come along and say, well, maybe there's a different polynomial. Maybe there is a polynomial which describes it, right? How could you rule this out, right? And there must be some elementary algebraic geometry argument which possibly proves that. I just don't know it.
For example, if you look at the function e to the power x minus e to the power y, that doesn't look algebraic, but the surface cut out by it would be the same as x minus y.
I think when we talk about algebraic, we fix to this Cartesian coordinate system, and then because but that's what I said. If you're doing change of then every set will smooth surface will look like an algebraic. Okay, so so for the same reason, you can also see why catenoid is not an algebraic surface. The usual catenoid in E3, which you have a hyperbolic cosine. And so we have this lemma. So what this lemma says, like the generative curves which we have seen right now, we know the formulas. Using those formulas, we can associate because those formulas will give you a family of CMC surface of revolution in L3 around, let's say, z-axis in this case. So this family of CMC surfaces of revolution, it will identify a family of elliptic curves. So when I'm saying elliptic curve, I'm just thinking of an equation like this. So this is what. And in this case, in my case, it is ABC are allowed to be complex numbers. So so this is so people study algebraic curves over different field, but in our case, they're going to be complex at the most. And of course, you say such an elliptic curve is smooth if one can compute, one can define the discriminant of this, and if this discriminant is non-zero, you say the corresponding elliptic curve is smooth elliptic curve. So so when I say this will identify a family of elliptic curves, I mean to say we will get a smooth elliptic curves. So what is the idea? So I'm very briefly, I'm skipping many details. So what we can do, because see, our goal is to associate some elliptic curve. So I just want to get through those parametrizations something like this, some equation of this sort. And then just somehow try to show that the equation which I'm seeing there, this is an elliptic curve, and then the discriminant for that is going to be non-zero. So the idea is you do change of variables. So by doing multiple change of variables in this, so you start with the Z component, this ZS, which is like this. So by doing some change of coordinates, we will arrive like this. We have an integral like this, and then you define this L to be this number, M to be this number, and N is this, and you have to choose C to be this. There's all reason for that, doing such a thing. But yeah, ultimately it's just doing change of variables. You see, we will get this. Means what I'm saying, the equation which you see here is actually this when you put L, M, N there. So we are seeing this equation, and now we just want to put V square is this. So this is something we have. This is anyway, it is going to be positive, so there is no problem there. And again, you just even if you're not applying this transform, that's okay. But you know, this is kind of a standard way of writing an elliptic curve. So you can do again further transformation to convert this equation to this particular equation. And now the claim is this represents a family of non-singular elliptic curves. And this family is parameterized by B. So you can see everywhere there's a B. Even C depends on B. C you see here. Okay. So this is a family of non-singular elliptic curves. Why this is family of non-singular elliptic curves? And of course, for when V is not 0 and 1, because 0 and 1, you see those integrals are, you can easily integrate, and you can, there is a cylinder and the sphere. Okay, so yeah, so this is the theorem. So this theorem is now, we will show that if you are just thinking of a space-like CMC surface of revolution in L3, whose axis of revolution is a time-like axis, then this cannot be algebraic. So you have this whole family which includes the space-like cylinders and standard hyperboloids also. So means what I'm saying that this nodoids and the unduloids, they are not algebraic. Okay, so yeah, so the thing is like now the elliptic curve which I have shown you in the last slide, we can compute its discriminant, and the discriminant turns out to be this. And you can see that this will be 0 precisely when B is 1 or minus 1. But minus 1 is not in our set, so if you put 1, anyway, B equal to 1 case, we are not considering, because B is equal to 1, we already have this sphere. So for all other values, so 0 is anyway not going to be something which will give 0 here. So this discriminant is non-zero, and this shows that the elliptic curves there which I've shown you, they are all non-singular. And now again, what to do with this? So whenever you have so there's again, this is a fact, like whenever you encounter an elliptic curve, there is a very well-known result which says that you will get a lattice. So whenever you have an elliptic curve, you will get a lattice in the complex plane, so that there's something which can define as that the lattice corresponding to that lattice, there will be these two things, G2 and G3, which will assume those coefficients value. And whenever you have a lattice in complex plane, there is a Weierstrass P function. You can define a Weierstrass P function, which is a W periodic function on this lattice. And so what I'm saying, corresponding to every elliptic curve, this tells you that this theorem tells you that this result, that there is a Weierstrass P function, which will satisfy an equation like this. Okay, and now the point is these are the key. These relations are the key. So now what we are going to do? Okay, first let's see. Once you have this, we can also. It's not very difficult to see that we can differentiate this. But just by noting that you can choose a point, or you can you pick a point, and you can always get a neighborhood of that point, so that in that neighborhood, if you are just restricting this P, the derivative will always be non-zero, so that you can differentiate it. So once you differentiate it, you get this relation. And yeah, now here I have skipped many things. Now the point is, now we want to replace these W and V, which we had in that parameterization for ZS, by this PZ tilde and P prime Z tilde, because this is how we are getting from those things. So once we will replace these things, and then of course when you're replacing this, because now this is a Weierstrass P function, which are kind of complex valued. But the point is, again, by using some properties of Weierstrass P functions, like the Weierstrass P function, if Weierstrass P function takes values, real values, it can only take real values along either x-axis or the purely imaginary axis. There are no other points. So what you can do, because you have to kind of go back and forth between these two variables. So we can certain, so what I'm saying, the integral which you see here, I'm writing this t naught t, and then now there is this Weierstrass P function. So how come we are getting this real integral? Because we want all these things to be real. And that is taken care by the properties of Weierstrass P function, that we will not encounter any complex thing here. So we will get some zt. We can reduce those, yeah, there's many things there in between, but you can reduce this zt like this, and the same line, you can start with xt, which you had earlier. You will see xt will convert, will be equal to this. And this p, where p is something like this constants. And now again, I have to, so now here's the trick. So we have gotten these xt and zt in terms of Weierstrass P function. And now we have to recall one fact, like if you have a surface of revolution, let's say in a space in R3, then one can show that that surface, the zero set of such a surface, or that surface of revolution can be described as a zero set of this function, a function of this form, x square plus y square minus z square, r of z in this case, where this r is kind of height function. Like when you look at the curve, so this r is this radius parameter, which kind of vary, which depends on z. So the claim is, so now you can see, if you know this, so now you know any surface in that family will have this form. So in order to show that those are not algebraic, the underlights and nodalights are not algebraic, it is enough to show that r of z is not going to be an algebraic function or some polynomial. So that's what we want to do. So what we will do, we will go by contradiction. So let's assume that r of z is a polynomial in z. What happens? So if r of z is a polynomial, then what we can do here, we can differentiate this r of z. So r of z from that earliest, from here you can see r of z, sorry, is this. And also implicit, we can see that the t will be a function of z in some sense. So we can take the derivative of this p with respect to z. So when you differentiate this equation, assuming we have assumed this r of z is a polynomial for now, and we want to arrive at a contradiction. So if you assume this is a polynomial, and when you do the derivative, differentiate this with respect to z, what you will see that when you take the first derivative, this is what you see. R1p times p prime. What is R1p? It's just a rational function of p. Some expression which is just a rational expression in p, and then you have this p prime. And when you take one more derivative, you will just simply have this rational function of p. There's no p prime. And in fact, this pattern will continue. Like at odd states, you will encounter a factor of p prime, and at the even states, you will just simply have a rational function of p alone. But the point is, since we have assumed this r of z to be a polynomial, so there will be a space, because if you have a polynomial, this will have a finite degree. So you will get some natural number so that this derivative will be 0. And of course, this m will depend on the degree of the polynomials. In any case, what happens? Suppose if m is even, the degree of the polynomial is even, then because we know that this is what we get at even states, and then there is simply, you see algebraic relation. So this implies what you see, that p satisfies this, there is an algebraic relation which is satisfied by p, which is not true. And this showed that p is a transcendental. And now if m is odd, you can have something like this. But again, you can again choose a point, and you can show that you can shrink the neighborhood so that in that neighborhood, this p prime will be not vanishing. And if it is not vanishing there, then This product is 0, that means this is vanishing. So again, you have shown that this satisfies algebraic relation. And so you arrive at a contradiction, and we have shown that the space-like surface of revolutions about a time-like axis cannot be algebraic. And exactly a similar argument one can apply to deal with the case of when you have a space-like CMC surface of revolution about a space-like axis. And so you know at least in L3 in this class these are the examples. And now our method works for in E3 also. So what we can show on the same line, like if you're looking for non-zero CMC surface of revolution in E3, then these undulates and nodoids are not algebraic. So in some sense, because this, I don't know, because when you talk about regular algebraic surfaces in E3, this spheres and cylinders are known to be algebraic. But this theorem doesn't say about anything about which is not, surfaces which doesn't have a self-intersection. But you can see here, at least in this class, the nodoids are kind of examples which have self-intersections. And we are sure now that they are not algebraic. So at least we know for some examples of CMC surface that they are not algebraic. That's it. Thank you.
Are there any questions?
In currents, we use this theorem to contradict something if something is not algebraic. So something is not algebraic, a line intersects it at infinitely many points. It's enough. That's enough to claim that curve is not algebraic. So for example, when you are undulated surface, could we take a plane and say that it is intersecting in infinitely many one-dimensional disjoint surfaces, curves, which is again
A plane intersecting undulates at infinitely many times. Yeah. Yeah. Yes. Infinite. Yeah. Yes. So what does Bezos theorem says? Like if you I think something that sort, something can be done like this, because what I have seen, the papers which I have seen or referred to, in some of the papers they do use the techniques from algebraic geometry. And there is, I think, in one of the paper they also use Bezos theorem at some point of time, but I'm not sure. The point of my work was we saw that the class of this CMC surfaces, they also identify something very analytic, like Weierstrass P function. Yeah.
Any other questions?
Thank you for a beautiful talk. I have a very basic question about the beginning. When you show the N-per surface, so it's parameterized by polynomials. So first question, that means it's obvious that it's algebraic, I assume. And how do you get, then you said it's degree 9, how do you get from the parameterization to the polynomial, to the equation?
Yeah, it can be done. You have to do...
but you have to do some work.
It's a lot of work.
Okay.
Yeah,
okay.
One can try.
Okay, thank you.
Sorry. Can you draw some CMC surfaces in L3 explicitly to see how does it look like? For example, the space-like cylinder, how does it look like?
So you imagine this hyperboloid. So the equations which I wrote, okay, let me just show you this equation. So this is like kind of this branches, and then you kind of rotate in L3. So it will generate.
Oh, okay, okay, yeah. Thank you.
So you look at the generating curve and then you have to rotate.
Yeah, thank you.
Any other questions for the speaker? If not, let's thank Rahul again. Right, so I guess now it's lunch and we'll resume at 2:30.